Alright, welcome back to another college algebra final review video. In this video, we are going to be going through another 25 practice problems just as we did in the part 1 video. Okay, so if you haven't watched that video, I would definitely check it out. That's problem 1 through 25, and in this video we'll be doing 26 through 50. And by the way, I do apologize, I should have got this video out a lot sooner, but I had my own finals that I had to get through, so that definitely took a lot of time out of my day. But anyways, let's just jump right into this. So in this video, our 25 problems are going to be on the following topics. First, we're going to be talking about the inverse of functions. We'll be doing a couple problems there. Then we'll be doing a couple problems on the compositions of functions. We'll be talking about graphing functions, transforming functions. We'll do complex numbers, rational functions, which a rational function is basically just a polynomial over a polynomial. And I'll talk more about that when we get to that section. But we'll also be talking about exponential equations and functions, and we'll also be doing, lastly, logarithmic equations and functions, okay? And I have all the timestamps on the left, of course, in case you want to jump to a specific topic that you definitely think that you are struggling on, okay? So without further ado, let's hop into our first problem, okay? And that problem is on the inverse of functions. Okay, so we want to find the inverse of the function f of x equals 1 over x minus 4. Okay, so what does it mean to take the inverse of a function? All right, you may think of inverse and think of that -1 that's in the exponent, right? But that's not really the whole story. Okay, so if you take the inverse of a function, right, we have y equals 1 over x minus 4. Okay, all we have to do to find the inverse of this function, right, and basically what I mean is to find f prime, or f to the -1 of x. Okay, that's the notation for the inverse. What we do is we just switch the variables. Okay, so the x goes where the y goes, and the y goes where the x goes. Okay, and then when we're in a certain situation like this, all we do is we just solve for y. Okay, and once we solve for y, we have that inverse function. Okay, so we just got to solve for y here. All right, but the biggest part I think that a lot of students struggle with is just getting this transformation down. That's how you start out this problem, right? And if you are able to start the problem, it's a lot simpler from here on out. Okay, so something I like to do when you have two fractions that are equal to each other, you can think of this as x over 1 equal to 1 over y minus 4. You can actually move these two, you can move this thing diagonally, you can move like any piece diagonally, okay? So I can move this x down here, and I can move this y minus 4 up here, okay? And to prove that, okay, what you can do is you can multiply both sides by y minus 4. Okay, and if you do that, you get y minus 4 times x equals 1, right? Because this will cancel over here. Okay, and then you can just divide each side by x and get y minus 4 is equal to 1 over x, right? And so if we look at what our original equation was, okay, we could have just moved this y minus 4 up to the numerator on the other side and moved this x down to the denominator on the other side. Okay, and if you did that, you would get this. All right, you can think of this as y minus 4 over 1, so same thing, right? Now, all you have to do to solve for y here is just add 4 on both sides, and we get y is equal to 1 over x plus 4. Okay, and that is the inverse function. So we can rewrite that as f inverse of x equals 1 over x plus 4. All right, and that right there is our answer. Okay, so that is problem 26, right? The reason why I'm calling it 26 is because we had 1 through 25 in the last video. All right, anyways, moving on to our next problem. We are asked if we can invert the function g of x equals x squared. Okay, now how do we know if we can invert a function? Okay, well, we can invert a function if it's both 1-to-1 and it's on 2. Okay, so we got to start checking for this stuff. First, let's just check to see if it is 1-to-1. Okay, now what does it mean to be 1-to-1? Well, if a function is 1-to-1, that means that it passes the vertical. The easiest way to remember this is it passes the vertical and horizontal line test if it is 1-to-1. Okay, so let's just graph x squared. Okay, and to do that, I'll just switch the paper type to a graph. Something I did not know I could do until this video. So we'll draw our axes. Okay, and draw x squared. Okay, so this is g of x. Now, if it first off, does it pass the vertical line test? In other words, can you draw a line through it and anywhere on the graph and have it pass through the graph twice? If it does, then it fails. Okay, well, no, if we just draw lines through this graph, you can see that it only passes through the graph once. Right here it passes through there, and then right here it passes through right there. So it's only passing through one time. So it passes the vertical line test. Okay, but what about the horizontal line test? Well, that's basically the same thing, but with a horizontal line. And you can see that if you pass a line through horizontally, it passes the graph in 2 places. Okay, so there are multiple x values that have the same y, and that means that this function is not 1-to-1. Okay, and what that ends up meaning is that this function is not invertible. And we can write that as, so we can say, no, you cannot invert g of x because it is not 1-to-1. We know this. If you want to add an additional explanation, we know this because it fails the horizontal line test. All right, and that is that. So problem 27 is complete. Now we're going to move on to our orange section, okay? And this is on the composition of functions, okay? So what do I mean by composition of functions? Well, basically, when you're composing 2 functions, you're talking about that little circle guy right there, okay? And basically what that means is that you have a function inside a function. Okay, you're sticking a function inside a function, and if you have multiple compositions, it's a function inside a function inside a function, and so on. Okay, so what do I mean by that? That seems kind of weird, right? It definitely was when I was learning it. I was like so confused with the composition of functions. But what basically, you can rewrite this whole thing as f of g of 2. Okay, now if all that notation confuses you, I'll write it with colors to make it look a little nicer. Basically, generally you have f of x, right? Or whatever your variable may be. Well, now that x is g of 2. Okay? And that's literally it. So your input of f is going to be whatever g of 2 is, right? And we'll find g of 2 in just a second here, but I want to make sure that you understand how to convert. Let me grab my highlighter here. I want to make sure you understand how to convert this to this. Okay, and really, yeah, keep it in the exact same order. Okay, and then take out this circle and just put a parentheses in there. Okay, and then take out that one, right? And then you pretty much have it right there. That's kind of what I would do. I mean, really, it's kept in the exact same order. Okay, so now that we are hopefully all on the same page there, let's find g of 2. g of 2 is basically just going to be us plugging in 2 for x here, right? If we plug in 2 for x in this equation, right, we get 2 squared minus 3. Okay, we plugged in this 2 right here. So we have a 4 minus 3, and that's 1. So we're going to plug that 1, since 1 is g of 2. This thing up here is equal to f of 1, right? So now let's find f of 1. F of 1 is equal to, well, we plug in a 1 here, right? Because that's f of x. So we have 2 times 1, and that's equal to 2. Okay? So this is equal to 2. And that is our answer. Okay? And if you want to write it out fully, then you can write it as this right here. Okay? So f of g of 2 is 2. All right? So you can write that in multiple ways. You can just, circle the answer, or, maybe your professor or instructor has a preference. Okay? So problem 28 is complete. Now we're going to expand on this a little bit. And remember, I said when we have a function inside a function inside a function, well, that's exactly what we're going to be doing in this problem. Okay? So it's just the composition idea, but expanded into you have an additional composition now. Okay? So let's take a look. This problem is asking us to find f of g of h of 1, where f of x is 3x, and g of x is 5x squared, and h of x is 1 over 2 minus x. Okay? So let's set this up. Well, we're going to have a f of, I'll write in different colors here. We'll do g of h of 1 and do that. Okay? So you can see that our input for g is h of 1. Okay? And actually, starting even at the first step, we're going to be plugging in 1 for our h of x equation. Okay? And that is going to, so 1 is the input for h, but h of 1 is the input for g. Okay, so that's what's going to be plugged in. H of 1, whatever that value is going to be plugged in our g of x equation. Okay? Then, whatever g of h of 1 is going to be plugged into our f of x equation. Okay? Again, g of h of 1, h of 1, these are all just numbers. Okay, they actually just all end up being numbers, maybe like, 5 or 7 or 1, and we just plug those in. Okay, that's all this really ends up being. All right, so moving on to problem 30 in our yellow section, and that's on graphing functions. And actually, before we get into the yellow section, every 2 sections, honestly, you should think about taking a little, like a 5-minute break, okay? Because I'm going straight through here and doing basically an hour and a half or 2-hour video, okay? So if you feel that you're kind of getting a little burnt out or something, like that's exactly me. When I study, I'll get a little burnt out and just take like a 5-minute break and then come back to the video, okay? And then you come back and you're more focused and it's more efficient that way, okay? So if you want to take a 5-minute break quick, definitely go and do it, and then I'll be right here, don't worry. Anyways, getting into this problem, is the function y equals 2x to the 4th minus x squared even or odd? Okay, so we got to review the idea of having an even function and an odd function. So an even function is when you have symmetry about the y-axis. In other words, f of x equals f of negative x. Okay, y equals x squared is a example of an even function. Okay, so remember, when you have y equals x squared, we're talking about something like this, right? And you can see that has symmetry about the y-axis, right? If you flipped this piece, right, if you flip that over the y-axis, you get this piece. So it does have symmetry over the y-axis. Okay, they're exact replicas on both sides. Okay, so basically, if you have f of 2, right? If you're talking about y equals x squared and you have f of 2, plug in 2 for x, and you would get 2 squared equals 4, right? So you know f of 2 equals 4, but what about f of negative 2? Well, if you have y equals x squared again, you plug in negative 2 this time, and you square negative 2, well, negative 2 times negative 2 is positive 4. So you get the same exact y value. You get 4 for both, right? So, and this is the same for all x values. Okay, so f of 2 is equal to f of negative 2. Okay, and this is an even function. That's the idea. Now with an odd function, what you end up getting is that negative f of x is equal to f of negative x. Okay, an odd function basically just means you have symmetry about the origin. In other words, if you have a point, let's pull up some graph paper here. If you have your axes here, okay, and you have some point right here, okay, so it's over 2 spaces and up 3. Okay, if you reflect this point about the origin, basically what you do is you just go 1, 2 this way and then down 1, 2, 3. Okay, so this point right here is 2, 3, and this point right here is -2, -3. Okay, let's say that this is all part of some graph that is odd. Okay, something like this. Okay, that is an odd function. Basically, the idea here is that, you know, at this point right here, negative f of 2 is going to be -3, right? Because f of 2 is 3, right? The y coordinate here at x equals 2 is 3. So you negate both sides and you to get negative f of x, and that gives you -3. Now for f of negative x, I'm talking about f of -2, and here you can see that that point is -3. Okay, sorry that took so long to set up, but yeah, you get -3 here and here, and so since those things are equal, it's an odd function. That's the idea. So hopefully that makes sense. So now we got to see that for, you know, y equals 2x to the 4th minus x squared. You know, if you're thinking about this graph, you know, trying to visualize it, it's not really going to make much sense to you, right? It's kind of hard to visualize a polynomial that has, it's up to degree 4, right? I'm not even sure what that would look like myself. Okay, so we're just going to plug in some values for x here. We know it's either even or odd, right? There's no really option for neither here. So honestly, we can just plug in one point. We can plug in, let's say, x equals 1 and x equals -1, and see what happens. Are these two things equal? Are they opposite of sign? And then we'll know if this function is even or odd. Okay, so let's just plug in x equals 1 into this function. Okay, when we plug in x equals 1, we see that, let's call this f of x. Okay, we get f of 1 is equal to 2 times 1 to the 4th minus 1 squared, and so you get 2 minus 1, and that is 2. Okay, so what about x equals -1, right? Because that would see if this function was even, then f of -1 should equal f of x, right? Or it should equal f of 1. So we have 2 times -1 to the 4th minus a -1 squared. And, well, what we get here is still, again, this is just 1, and this is, again, 1. So because these things are being put to a even power, so we still have 2 minus 1 here, and that is, sorry, this is not 2. I don't know why I marked that as 2. That's 1. Okay, I don't, wow, that's pretty bad. Okay, anyways, yeah, these are both 1, and that's a good thing. So that we know that this function is even. Okay, and just to make sure, let's try to plug in x equals 1, but make this thing negative. Okay, if we make this thing negative, what ends up happening is we get a, we know that, first off, f of 1 is 1, so f of -1, or sorry, negative f of 1 will be -1, right? Because we just multiply by -1 on both sides. So the idea here is that, well, -1 is not equal to this one right here, right? Because that's the criteria for an odd function. Okay, and so we definitely know that this isn't odd. Okay, so this is definitely an even function. Okay, and here's the giveaway, honestly. This function has even exponents. Okay, so you kind of know that this is going to be even. All right, and I'm not going to sit here and tell you that works every single time, because maybe you have certain shifts that, you know, will make it not necessarily even, but that's a pretty good indicator. If it's either even or odd, hey, this thing is even exponents, so this kind of makes sense. Okay, and that's kind of a nice little check for yourself. Okay. Moving on to problem 31, we want to graph the piecewise function below. And that piecewise function is f of x equals x squared when you have x between negative infinity and 2, not including either endpoint. And it equals 2x plus 1 when x is between 2 and infinity, including 2. Okay? So let's just set up some graph paper here, and let's go for it. All right. Oh, that's a highlighter. Let's see here. Okay. So getting this guy set up here. All right. We have two parts of a piecewise function. Okay, so that's what it definitely makes it a little harder to graph. And somebody, I definitely used to look at functions like this and go, what am I supposed to do with this mess? Okay, and basically all you're doing is you're graphing two functions on one sheet of graph paper. Okay, but you're limiting their domains. Okay, that's the idea. So we're graphing x squared, but we're not graphing it for anything greater than 2 or equal to 2. So the idea is, let's graph x squared. Okay, so we know that our points for x squared, it's going to come it's going to be right here, and then it's going to go up to here. Okay, and we can do that on the other side. Okay, and so coming down, we have this thing, and it's going to come right to this dot here, and and it's going to be an open circle right here. Okay, and we know that for x squared, when you plug in 2, you get 4. Okay, so that's why I knew to come up to this point. All right, so the idea is that we have this open circle here because we're not including this endpoint. If we were, there would be a line under it like I just drew. Okay, but there's not. So since we're not including the endpoint, we need to have an open circle. Okay, so now we have to do the other function. Okay, we have to do 2x plus 1. Okay, and the domain for this function is 2 to infinity. Okay, so what is 2x plus 1 going to look like? Well, what we can do is we can start at 1. Okay, and then we can go, because that's the y-intercept, and then we'll just go with the slope. Okay, we'll go, and of course we'll delete this eventually because this point is not in our domain, but we'll go up 2 over 1, up 2 over 1, up 2 over 1, and so on. Okay, and I guess this graph is kind of in the way here, so why don't I just move this, go up 2 over 1 again, and up 2 over 1. Okay, so we're just going to delete all the points that aren't in the domain. Okay, and notice we know that this point is in the domain because this includes 2. It has that bar under like I showed. Okay, since it has that bar under, we know that this endpoint is included, and so we're going to have a closed circle here. Okay, and so we'll just draw a line through here. Okay, and that is our piecewise function. That is f of x. Okay, and we can label it, y equals f of x. Okay, so that is the idea with a piecewise function. Really, you're just graphing two separate things, but they have different domains. Okay, you're restricting the domains, and if you can get past that fact, really the graphing isn't that tough. Okay, you can set up an XY chart if that went a little too fast for you, and you can go through it that way. Not a big deal. So for problem 32, we want to graph h of x equals x squared minus 3x plus 2 using complete the square. Now, why would I ask you to use complete the square for graphing a parabola? And it's not because I'm a jerk, it's because sometimes that's the way to go. And the reason why is because completing the square can be really efficient compared to creating an XY table. Okay, if your vertex of your parabola is way out at x equals 10, you won't know that right away with something like an XY table. Okay, so you'll definitely want to do something like completing the square to find the vertex of the parabola, then start there and kind of branch out and make your parabola. Okay, so let's complete the square here and see what our vertex actually is. When we do that, we get h of x equals, remember how we set up a complete the square problem. We have x minus, we're going to have a minus because there's a minus here. Okay, and basically the thing that goes here and gets squared is b over 2. So we have a 3 over 2. Okay, so the form is x plus b over 2 squared. Okay, here b is negative 3. We put it over 2, we get negative 3 over 2. Okay, but here's the deal. This is not the same thing as this, because if we were to expand x minus 3 halves squared, okay, well then we get x squared. We get a minus 3 halves x, minus 3 halves x, and then we get plus 9 over 4. Okay? And so this ends up being x squared minus 3x plus 9 over 4. This is not equal to x squared minus 3x. Why? Because you have this plus 9 over 4 here, and that's an artifact of simplifying it like this. So what you need to do is, since this is going to give you a plus 9 over 4, you subtract 9 over 4 here. Okay, and that makes it 0. So that factor goes away. Okay, and you can do that because now this thing is equivalent to this. Okay, and since those two things are equivalent, now you just put a plus 2 on the end. And you can simplify this now. I'm getting an x minus 3 over 2 squared. You can convert 2 to 8 over 4 and get minus 1/4. Okay, so now you have it in vertex form. You know that your vertex here is h comma k. Remember that this is your negative h, so you have to flip the sign, and so your h is 3 halves. Okay, and your k is negative 1/4. Okay, and that is going to be your vertex. Now this is going to be a really nasty graph, so what I'm going to do is I'll spare you the trouble and not go through a whole xy table with you. But the idea is that since that's your, and actually, you know what? That's another reason why completing the square is actually really nice, because you wouldn't, when you do an xy table, generally people don't do like, they don't do like 3 halves. They do like x equals 1, 2, 3, 4, 5, or negative 1, 2, negative 3, negative 4, but they don't do like 1/2, 2/2, or 1/2, 3 halves, 5 halves, all that stuff, right? So that's why completing the square can be really, really good for quadratics. Okay, so maybe a better title for this problem would be to just kind of roughly sketch this graph. But what we can do here is if we set up our axis here, okay, and we make each point worth on the x, we'll call this, call it 1/4. Okay, so actually I'll write that in white. So this will be 1/4, 3/4, 5/4, 7/4. Great. And then this will be down here. This, like, we'll do it the same way on the y-axis. Okay, so that way we know that 3 halves, that's 6/4. So it'll be, our vertex will be right here. And we know that this is a upward facing parabola. Okay, the reason why we know that is because the coefficient on x squared is 1, which is positive. Okay, so if it was negative, right, if it was a negative x squared, then we would know it would be downward facing. Okay, but since it's a positive, we know it's upward facing. Okay, so just roughly sketching this parabola, it will look like that. Okay, so if it wants you to actually graph it on graph paper, then you can't really just do exactly what I did there. I was kind of just trying to to cheat with it for time's sake, but you understand the idea with completing the square. You find the vertex, and then, okay, is this upward facing or downward facing? And you have a brief idea of what this graph looks like. And that's why completing the square is really nice. Okay, so moving on to problem 33, we want to, and I'll switch back to like a normal graph paper here. We want to state the transformations done to y equals the absolute value of x to obtain the function below. That function being d of x equals -3, the absolute value of x plus 2 minus 4. Okay, so basically the idea with this transforming section is that we start off with some graph y equals the absolute value of x, and we apply a series of transformations to get it to be this thing down here. Okay, so we have to ask ourselves, like, what are those transformations? You know, what happened? Well, if we kind of go in order of PEMDAS, we can start stating out these transformations. Okay, the first thing is that, well, you can kind of think of these absolute value signs. They're kind of synonymous with parentheses in a way, right? So they're, if you have PEMDAS, right, absolute value kind of comes in first there with parentheses. But the idea is that you can, sorry, not d of x. You can say that your first transformation is that this was shifted left 2 units. The reason why? Because this is positive. It's positive 2. So you make it negative because it's inside those parentheses. Okay, and absolute value, same idea. Obviously, absolute values do different things, but hopefully that at least makes sense. Okay, well then you have a 3 outside here. Okay, this, we'll ignore the fact that it's -3 for now because the negative does something different. But this 3, okay, since it's outside being multiplied, is going to produce a vertical stretch by a factor of 3. Okay, and hopefully this whole concept, all the, the idea of transforming functions is starting to come back to you now. If it's not, then this is definitely something you want to look into a lot more. Okay, but we took care of the 3. Now we have this negative as well. Okay, and that kind of goes right in with our second step here. But basically what the 3 does is not only is that the -3 as a whole is producing a vertical stretch by a factor of 3, but since it's negative, it's also reflecting the graph over the x-axis. Okay, that's what that'll do. If you have something like instead of saying y equals x squared, if you say y equals -x squared, well, what you've just done, and we talked before about upward and downward facing parabolas. Well, what you've just done, instead of having something like this, you have something like this. Okay, so it reflects it over the x-axis. This is the x-axis. Okay, cool. The last thing that we have to account for is this -4 here. Okay, and that's kind of the last thing on PEMDAS, right? We think about this. We talked about absolute value is kind of in the same category as parentheses, right? So that got canceled off first. We don't have any exponents. We have -3 being multiplied, and we took care of both the negative and the 3 separately. Okay, no division. We have no addition, and we have subtraction last. Okay, so subtraction is right here. We have a -4. So what this is going to do is a shift down 4 units. Okay, and that is the 4 transformations that were applied to y equals absolute value of x in order to get this d of x function. Okay, so that's the idea. Just kind of go through with PEMDAS, see what different transformations are being applied to that y equals absolute value of x, or whatever that function may be, and that's it. Okay, moving on. So now we are going to be on problem 34, and we just want to find the equation of y equals x squared after it has been shifted right by 3 and up by 2. Okay, so kind of the opposite thing here. Okay, so we have 2 transformations that are being done to it. Okay, it is, we have that y equals x squared is being shifted right by 3 and is being shifted up by 2. Okay? So we start off with that y equals x squared graph. And if we're shifting right by 3, what are we going to do? Well, we want to create parentheses, right? Because that's how you get your left and right shifts, is you have you put your transformation inside the parentheses, right? So we have x minus 3 quantity squared, okay? And that gives you your right shift, right? And remember, we have to switch the signs. So right, you would think is positive, but instead you make it negative, okay? And the same does not follow for shifting up and down. So here it actually would be plus 2, and that would be on the outside, okay? So inside the parentheses, you get a left-right shift, and outside, you get that up-down shift, okay? If there was something being multiplied by here, like a 3, that is a vertical stretch. If you make it 1 over 3, then you have a vertical shrink. Okay? So, there's a bunch of different transformations to know there. Okay? But they all, make sense, right? Of course, you can also think about this with vertex form, right? With completing a square. We always have to flip the sign here inside the parentheses. Okay? So that's the idea here. And actually, I think yeah, that was our answer, actually. And I was marking that up. Okay? So yeah, this is our answer. Great. So now we want to actually graph that function. Okay, we want to graph the function that we found in problem 34. Okay, well, let's go through and do that. Remember, that function was y equals a x minus 3 quantity squared plus 2. Okay? And we can do that. Okay, this is kind of just like that one problem before that we did. Okay, that which problem was that? Yeah, this problem right here, problem 32. Okay, where we're graphing something and that's in vertex form. The function that we're given here is in vertex form. We know our vertex is, well, we can go over 3 and go up 2. And this is the vertex of our parabola. Okay? So, now, we know that this is a upward facing parabola, okay? So, if you wanted to just roughly sketch this graph, you can just say, okay, well, there's your upward facing parabola and call it good, okay? And that's what I would do, because we wouldn't, for the classes that I take now with math, we don't really need something. We just need to understand what a graph looks like, honestly, and that'll help us do the main problem, okay? But anyways, I'll actually go through here now and do an XY table with you. Okay, so let's set up our XY chart. Okay, and I'll actually do that right here. Okay, this will be our x's, this will be our y. Okay, so we're just gonna just draw some lines. We'll go around 3. Okay, so that'll be our midpoint, and we'll do 5 points. Okay, so 3 we know has a y coordinate of 2, right? That's what our equation tells us. And then we'll just do 2 and 1, and we'll do 4 and 5. Okay, so for 2, we know that if we plugged in 2, we'll call this f of 2. Plug in 2 here, we have 2 minus 3 squared plus 2. This is going to be a negative 1. When you square that, it's just 1, and when you add 2 to that, it's 3. Okay? I hope I'm not going too fast here, so I apologize if I am. If we do f of 1, that is going to be a 1 minus 3. You're going to square that and add 2. 1 minus 3 is negative 2. If you square that, it's 4. And you add 2, it's 6. Okay? And then we'll do f of 4 and f of 5. Now f of 4, you're just going to plug in a 4 in here. And you get 4 minus 3 is 1. You square that, it's 1 still. And you add 2, and that's 3. And for f of 5, you plug in 5 here. 5 minus 3 is 2. You square that, it's 4. Add 2, it's 6. Okay? And so now you have your other points that you can put in. And you can put in up here. And then there you have a much better graph. Okay? Not just something that's a rough sketch like we did in 32. We have, a real legit graph here. Okay, with the points plotted, exactly with an XY table. Okay? So that is the idea with transformations. So now we're going to be moving on to complex numbers, okay, and that's problem 36 again. Now we are at, we've done another 2 sections, so if you want to take a break, okay, then definitely take a 5-minute break, come back to the video, and then we can get going on another 2 sections here, okay. Assuming that you've done that, let's hop back into this video, okay, and now we're going to be going on our complex numbers topic, okay. And, don't let the I stuff scare you. It's not a big deal. Okay, well, there's just a couple different things you have to remember. So for this problem, we are being asked to find the product of 2 plus 5i and its conjugate. And if you are having trouble with this problem, if you're trying these problems on your own, which I do recommend, I should have told you that at the beginning of this video. But if you're having trouble with this problem, it's probably because you don't know what a conjugate is. Okay, the idea is that if you are trying to take the conjugate of a complex number, you're just going to negate one of the terms. Okay, so the conjugate of 2 plus 5i is 2 minus 5i. Okay, if you have the conjugate of a minus ib, if you have the complex number a minus ib, the conjugate is a plus ib. Okay, and if you had something like 3 minus 4x, the conjugate is 3 plus 4x. Okay, so hopefully you start to see the pattern here. All right, so if we're trying to find the product of these 2 complex numbers, okay, a complex number multiplied by its conjugate, you'll start to see why we multiply complex numbers by their conjugates, okay? And you'll see here we have 2 times 2, that's 4. 2 times minus 5i, that is negative 10i. 5i times 2 is positive 10i. 5i times negative 5i is going to be negative 25i squared. Okay? And the reason why, and now you see it, the reason why we multiply a complex number or anything in general by its conjugate is because the middle terms will always cancel out. Okay? And now we're left with 4 minus 25i squared. Now it's also interesting when you multiply a complex number by its conjugate, okay, you make it a completely real answer, and you may not think so because we have an I squared here, but this actually ends up being a real answer, and the reason why is because I squared is equal to negative 1. How do I know that? Well, we know that I is equal to the square root of negative 1, right? And if you square both sides, well, a square will cancel out a square root, right? So you get I is equal to negative, or I squared is equal to negative 1. Okay? And that's the idea. So I squared, you can just substitute that in with negative 1. So you would have a negative 25 times negative 1. That just ends up being 4 plus 25, and that gives you 29. Okay? And that is your final answer. It's 29. Okay? So to go over that again, the idea of, the whole idea of multiplying something by a conjugate is so you can cancel out those middle terms. It makes it a lot nicer. It's especially nice for complex numbers because when you multiply, those middle terms are the only imaginary parts of what you just multiplied, okay, of your product. So when they cancel out, you are left with a completely real answer, meaning there's no imaginary stuff in it, okay? That's the idea. Moving on to our next complex numbers problem, we have -3 minus I minus a 6 minus 7i. Okay, and this is just combining like terms. Okay, it's the same exact thing if you had something like -3 minus x minus a 6 minus 7x. Okay, it's the same exact thing. Okay, taking that into account, basically what we can do here is just distribute this negative. Okay, make sure you do that. And I'll get rid of these parentheses. So we'll have a -6, and this negative will go to the -7i and make it positive. Okay? So this is a -3 minus 6, and that's -9. And then we have a -I plus 7i, and that's a plus 6i. Okay? And that's really it. That's how you combine complex numbers. Okay, you're just combining like terms, just like you would with x's. You see that if we do this with x's, let's write this as -3 minus x, and we'll distribute the negative again, -6 plus 7x. We get the same thing. This is -9 plus 6x, right? So it's the same exact thing. Moving on to problem 38. Now, I'm not sure if this is something that you have definitely done. I know a lot of college algebra courses incorporate different things, but if you have divided complex numbers before, this is definitely a good problem for you. Okay, the idea with dividing complex numbers, and for this problem we have 7 minus I over 2 plus 10i, is that what we want to do is multiply by the complex conjugate on top and bottom. And it's the complex conjugate of the denominator. Okay, so let me write that down to make it crystal clear. Okay, when dividing complex numbers, all you have to do is multiply top and bottom by the complex conjugate of the denominator. And this is a big thing. It's of the denominator, because you want your denominator to become real. All right, so that's the idea, and I tried to make certain things stand out here by just like marking them as like blue, but that didn't really work because I ended up marking too many things in blue. So I could have just like made that white, but whatever. I'll know for next time. So anyways, yeah, let's get to it. Let's multiply top and bottom by the conjugate here, and the conjugate of the denominator is 2 minus 10i. So we're going to multiply that by top and bottom. Okay, so 7 minus 10i times 2 minus 10i, and we have a 2 plus 10i, 2 minus 10i. Okay, so first off, let's do the denominator, because that'll be easier. You have a 2 times 2, that's 4, and you have a 10i minus 10i, or 10i times negative 10i, and that'll give you a minus 100i squared. Okay, now note that we don't need to care about the middle terms here. Remember when I showed you this in problem 36, right? When you multiply two complex numbers that are conjugates of each other, the middle terms cancel out, the I terms cancel out. So really we can just leave it as that, as the 4 minus 100i squared. And remember that I squared is -1, so this I squared goes away, and we can just make that positive. Okay, so we can also do this in the numerator, and that's going to be a little harder. We have 7 times 2 is 14. We have a negative I times negative 10i gives us plus 10i squared. Then we have a 7 times negative 10i. That gives us negative 70i. And we have a negative I times 2, which gives us negative 2i. Okay, simplifying a little bit here, we get, well, first off, this is going to be a negative 10. So we just get 4 minus 72i. And then in the denominator, we get 104. And we can simplify this here. I'll save you the hassle here. I'll just simplify it for you. You can divide everything by 4 and get a 1 minus 18i over 26. Okay, you already know that you can take a 2 out of everything because they're all even numbers, but you actually can go all the way up to 4. Okay, so if most likely if you're assigned a problem like this, they want it in the simplest form possible. Okay, so you're going to want to simplify this into that. Okay, but that's really the idea. Remember, when you're dividing complex numbers, you're just multiplying top and bottom by the complex conjugate of the denominator. Okay, we did that here. That was the conjugate. We multiplied it on top and bottom, and we got, we went through the process and simplified down to our answer. Okay, so moving on to our next section, we're talking about rational functions. Okay, and basically what a rational function is just a polynomial over a polynomial. Okay, here we have 4x plus 5, that's a polynomial, and x minus 6 is a polynomial. Okay, so another example would be 2x squared plus 4x plus 6 over x squared plus 3x plus 5. Okay, so that's what a rational function is. And for this problem, we want to state all the asymptotes of this rational function. Okay, so the 3 different categories of asymptotes that we have are vertical, horizontal, and oblique, or you can call these diagonal. Okay, if we just look at vertical first, well, for a vertical asymptote, okay, that's just going to be where the denominator is 0. You can see here that the only place that's going to happen is where x equals 6. Okay, now let's talk more about horizontal asymptotes. Well, basically the idea, and this is actually something good to write down, and that's why I wrote that down right here. Horizontal asymptotes are going to occur when the degree of the top is less than or equal to the degree of the bottom. Okay, so that is, for those of you that don't know what degree is, the degree of the top is the power, the highest power of x in the top. So here that's 1, right? Because you can think of this 5 as 5x to the 0, right? So it's, and x to the 0 is 1, right? Anything to the 0 power is 1. But the idea is that, yeah, the highest power of x in the top is 1, so it has a degree of 1. And the same goes for the denominator. The highest power of x is 1, so you have a degree of 1. So here, the degree of the top is equal to the degree of the bottom. And so we do end up getting a horizontal asymptote. Okay, because it's less than or equal to, right? So it's equal to, so that's a horizontal asymptote. So we're going to get one. We'll have to take a look at that in a second, but also good to write down when you get oblique asymptotes or diagonal asymptotes, right? That will occur when the degree of the top is greater than the degree of the bottom. For instance, if you had something like 2x squared over x, right? Here, the degree of the top is greater than the degree of the bottom. The degree of the top is 2, the degree of the bottom is 1. Okay, so that's the idea. So we won't get any oblique asymptotes. We can write down none. But we will get horizontal asymptotes. And how do we figure out what that horizontal asymptote is going to be? Well, the idea here is that we just have to compare, we have a degree of 1 on top and bottom. Okay, so we're just going to look at that. We have a degree of, or we have the coefficient of 4 on our x term in the top, and we have a coefficient of 1 on our x term in the bottom. So 4 over 1 is 4, and that will be our horizontal asymptote. That's exactly how you do that. Okay? If we had something where you had a degree that was larger on the bottom, like a x squared over x or something like that, right? So let's write that as x plus 3 so I don't have to simplify that. But here, you can just kind of picture having a 0x squared here. Okay, because you still want to compare terms that have the same degree. Okay, so here you would have a 0 over 1, which is 0. And so your horizontal asymptote would be y equals 0. Okay, if you had something, again, like x cubed over plus 1 over x squared, well, now you have oblique asymptotes and you do not have horizontal asymptotes. Because the degree of the top is 3 and the degree of the bottom is 2, and 3 is greater than 2. Okay, so hopefully that makes a lot of sense. Moving on to problem 40, we want to find all the intercepts of the function h of x equals 2x over x minus 2, x plus 1. This is, again, a rational function. Okay, we have a polynomial on the top, and if you expand this on the bottom, you get another polynomial. So this is a rational function. So we want to find the x-intercepts and the y-intercepts, and the easier one, right, if you're getting confused between the two, the easier one's probably going to be finding the y-intercepts, because where you cross the y-axis, your x is 0, right? That's the y-axis, is x equals 0. So if you plug in x equals 0 into this function, you're going to get your y-intercepts, okay? So let's actually do those first. So I'll move y-intercepts up here. And I'll move x-intercepts a little down. Okay, so we can find those y-intercepts by just plugging in 0 for x, right? Because we're looking at that x equals 0 line. And on top, we'll get 2 times 0. And on bottom, we'll get a 0 minus 2 and a 0 plus 1. So on the bottom, we're going to get a negative 2, right? Because we have a negative 2 times 1, right? This will be a negative 2 times 1. And on the bottom, or on the top, we'll just have a 0. So we'll get 0. So our y-intercept is just going to be at the origin. Okay, so at y equals 0. Now moving on to our x-intercepts, this is this is going to be a little tougher. Okay, we want to find where this function is going to cross the x-axis. And how we have to do that is by setting y equal to 0, right? Because the x-intercepts are where y equals 0. But when I said tough, I just meant a little bit tougher than finding the y-intercepts, right? And actually, that's kind of arguable, because here's what's nice about this. You know how I said you can move things diagonally? That was in the first problem, right? Because this is like 0 over 1. So you can move this denominator up to the numerator, right? And in which case, it would be 0 times that. You can basically 0 these guys out. So you can multiply this thing by x minus 2, x plus 1. If you do that, and so you multiply the other side by that same thing, x plus 2, x plus 1. So this is not x plus 2, it's x minus 2. Okay, and that zeroes it out, so you get 0 equals 2x, right? Because these go away. So you can literally just, it's really nice how you can do that. And so if you divide by 2 on both sides, you get x equals 0. And then that is your x-intercept. Okay, so we get a y-intercept of y equals 0 and an x-intercept of x equals 0. Okay, so this graph actually passes right through the origin. Kind of interesting. Okay, so the next problem we're going to be doing is finding the domain of the function j of x equals 1 over x plus 4 times x minus 1. Okay, so we want to see, well, is this graph completely continuous? If it's continuous, if through all x's, the domain is just going to be all x values. But And that's usually the case for like a polynomial like x squared, or x squared plus x plus 1 or something like that. The polynomial is all the polynomial's domain is all real x values. Okay, but it's not going to be the case for this rational function, because with anything being divided, you want to look where that denominator is going to be 0, because if that denominator ends up being 0, then you're in trouble, right? Because then you're dividing by 0 when that can't happen. So that's going to be a point that wouldn't be in your domain. Let me show you what I mean. This denominator is going to be 0 when x equals -4 and x equals 1. Okay? And so those points, okay, are not going to be in this domain, because if you plug in x equals -4, you get a 0 in the denominator, and you can't divide by 0. So that won't be a point on the function. So if you want to write the domain in interval notation, which I should have asked for specifically, what you want to do is just write, you start off from -infinity, right? And you have a parentheses there because you don't include infinities. You also don't want to include your next point, which is -4, because you don't have anything at -4. Remember, you get a 0 in the denominator. Okay? You make that a union with means it's kind of like your domain is this and this. That's kind of what the union does. The next thing, you'll go from -4 to 1, and then you'll do that from 1 to infinity. Right? And that basically just, what this does is it covers everything except for -4 and 1. Right? You can see the spaces here are because of -4 and because of 1. Because those are the places where you have a 0 in the denominator. So hopefully that makes more sense, and that is the domain of your function. Moving on to problem 42, and I forgot to label this section here, I apologize, but this was going to be the exponentials, like exponential graphs and doing all that stuff. So that's what this section is. We're starting here on problem 42, and of course, we've done another 2 sections at this point. So if you want to take a break, this will be a final time to take a break. Just take a quick 5 minutes for yourself here and just relax. So you're not burning out, because I've been recording this straight through and I'm already starting to burn out a little bit, to be honest myself. So take your 5-minute break and come back. Assuming that you've done that, let's get into this problem. We want to see which of these following graphs most closely resembles y equals 2 to the x. Okay, so we want to get an idea here of what y to the 2x is going to look like. And we can just create an xy table. We can do a bunch of things. So let's just check that out. Let's do an xy table and just see what graph makes the most sense. So we'll start at 0, and we'll just look at -1 and -2 and 1 and 2. Okay, so let's just take a look at this before we even compare to the graphs. Y equals 2 to the x. Remember, that is the graph that we're talking about here. Let's plug in 0 first, because that'll actually be a nice one. Anything to the 0 power is 1. So you know that 2 to the 0 is 1. Okay, so you need to have a y-intercept of 1. Okay, and so when we look at those graphs, hopefully they all have, or one of them has a y-intercept of 1. Okay, so now we can plug in, let's plug in 1. We will get 2 to the 1, and that's 2. So that is going to go right there. Now let's plug in 2 for x, and that gives us 4. Then we'll plug in -1. And remember what a negative exponent does, it just puts it, you can put it over like that. So it'll be 1 over 2 to the first power. Okay, so you can you put it, you flip it, right? So now instead of 2 over 1, it's 1 over 2. Okay, and you just negate the exponent. So instead of being -1, it's now 1. Okay, so this gives us 1/2. And then y equals 2 to the -2. When we plug in -2, we get a 1 over 2 squared, and that is a 1 over 4. Okay? assuming that that all makes sense to you, this is actually not going to be terrible moving from here on out. You'll notice that none of these points are negative. Okay, so we don't want, if we see any y's that are negative, like in this graph, right, this is all negative. So we know that C is not our answer. We also know that D is not our answer because we have negatives here. Okay, but these answers in A and B, we have all positives. The question is it which way is it flipped around the y-axis? We can see both here that we have y-intercepts of 1, right? So that 0 point works. But which way does the graph go? Well, you can see here that we have fractions on the negative side, right? So we have very small values. So you can see it works with A, not B, right? Because these are larger values. And you can see on the right-hand side, right, on the positive side, you're going to get larger values, right? 2 and 4. So you can definitely see that this is going to be A here, right? You can think of this as being something like 2, and then up here is like 4. Okay? But down here, this is like 1/2, and then where the arrow is pointing, that's like 1/4. Okay, so you can kind of think of it like that. All right, but hopefully that makes sense. Okay? The next thing that we are going to be doing is I believe this is called common bases technique. This is problem 43, and what we're going to be doing here is solving for x, where we have 25 to the x plus 3 power equals 125 to the x minus 2 power. Okay? And basically what we have to do here is, well, we realize that 25 is 5 squared. Okay? And if you rewrite it like that, well, that's to the x plus 3 power, and you call it good. And 125 is 5 to the third, and that is to the x minus 2 power. Okay? If you understand that, and you get your common bases of the exponents, right? These are the bases. Then you're pretty much done with this problem. That is the hardest thing to realize about a problem like this. Okay? If you can do that, you're good. So when you see something like that, like 25, you know that's 5 squared. 125, you know it's 5 cubed. If you had something like with, you had 4 to the x plus 2 equals 8 to the x plus 3, right? There's another problem you could try, right? You know that these are, like 4 is 2 squared and 8 is 2 cubed, right? And you can write it like that and solve that way. Here's why this is nice to write it like that, though. Because remember, when you have an exponent to an exponent here, so you just multiply them. That's the rule with exponents. So you have a 5 to the 2 times x plus 3 equal to 5 to the 3 times x minus 2. Okay? Since you have the common bases here, that means that these exponents are equal. Okay? And if you don't believe me, think about it. 5 squared equals 5 squared. It doesn't equal 5 cubed, or it doesn't equal 5 to the first or 5 to the 0, right? It equals 5 squared. The exponents, when you have common bases, the exponents have to be equal to each other. Okay? So we know that the exponent here needs to equal the exponent here. So 2 times x plus 3 needs to equal 3 times x minus 2. Okay? So we distribute here, we get 2 times x plus 6 equals 3x minus 6. We can subtract the 2x on both sides and add the 6 on both sides. Okay, so this goes away, this goes away. And now we have 12 equals x. Okay, and that's our answer. All right. Moving on, we have problem 44. And for problem 44, we want to state the transformation, which changes y equals 2 to the x into y equals 2 to the negative x. Okay, this actually kind of goes back to our graphing problem from before. This graph right here actually belongs to y equals 2 to the negative x. Okay, And you may wonder, okay, how do I know that? Well, it's a reflection about the y-axis. Okay, when you make a reflection about the y-axis, you're negating all of the x values. Okay, you can actually kind of think of it being it's kind of like similar to even functions, okay, where they're both reflection about the y-axis, okay, and you negate the x there, but that's kind of a different thing entirely. So maybe I shouldn't have even brought that up because I don't want to confuse you. But when you have something like y equals x squared and you negate the outside, so you have negative x squared. And since the exponent, since PEMDAS, right, the x squared will get to the x before the negative does. Okay, so this is a reflection about the x-axis. But when you have something like it's just the x being negated, this is a reflection about the y-axis. Okay, that's, I think, the most simple way I can explain that. Okay, so the transformation is a reflection about the y-axis. Okay, and showing you that for this graph specifically, well, if this graph was reflected about the x-axis, it would be y equals negative 2 to the x. Okay, and remember that x is in the exponent, so with PEMDAS, this negative wouldn't reach the 2 in time because the x is already, or maybe that's a bad way of explaining it. If you have negative 2 to the x, yeah, because of PEMDAS, the x operates on the 2 first. Okay, so that's the way I'll explain it. Hopefully that makes sense. For problem 45, we want to solve for x. We have 2 to the x plus 1 equals 5. Okay, and this is actually, I shouldn't have marked this as a exponential or a exponent problem. This is actually a logarithmic problem. So we're actually going to start with logs now. I didn't have my log. That's my log section down below on problem 46. But yeah, and I didn't even label it either. So I don't know what happened with the latter half of this video. But anyways, what we have to do to solve something like this is we just take a log of both sides. Okay, or we can take a natural log of both sides. That's generally what you do in higher level math. You deal with natural logs a lot more than you deal with logs. So, yeah, you can do either or. But we'll take a natural log of both sides, okay? And when we do that, we have a natural log of 2 to the x plus 1 equals natural log of 5. The reason why we take a natural log of both sides is because there's certain properties with natural logs, okay? You can bring the exponent out front. So this is x plus 1 times the natural log of 2, and that's equal to the natural log of 5. Why this is so nice is because now you can just divide natural log of 2 on both sides, and you get x plus 1 equals natural log of 5 over natural log of 2. Okay? And when you subtract 1 on both sides, you get x is equal to natural log of 5 over natural log of 2 minus 1. Okay? And that's your answer. Okay? So when you have an exponent problem and you don't see common bases, okay, that's when you want to think about logs. Okay? Because, and really I would check for the common bases first, because common bases can be really, really easy. But if you don't have something like that, you have a 2 and a 5, right? They're not there. 2 to the second is 4, not 5. 2 to the third is 8, not 5. So you can't really do the common basis stuff. Again, look for those natural logs. It makes it really easy, because really you're just moving the exponent out front and then you divide away. Okay, meaning you divide that natural log of 2 away and you're good, and you subtract the 1. Anyways, moving on to our what was supposed to be the full natural log section and logarithmic stuff. We want to find the value of log base 3 of 27. And the idea here is, if you write out the full thing here, it's kind of like log base 3 of 27 equals x, right? And we want to find what x is. Okay? So what we do here, and what I call this is circle trick. Okay, because you're going to move the 27 over here, you're going to move the x over here, and you're going to make this 3 bigger. And that's how you undo a log. Okay, I'll write that here. You can undo a logarithmic expression. A logarithmic equation, maybe. I'll write that down. Like this. Okay, and I'll write down simple because it has to be like it can't be. You can't use circle trick if you have something like log base 2 of x plus log base 4 of x, and then you have like over log base. Like it's not gonna. This is for something really simple like this. Okay. You can undo a simple logarithmic equation using circle trick. Okay, so when you do that, you get 3 to the x equals 27. Right? You make the 3 bigger, you move the x to the exponent of the 3, and you move the 27 over. Okay, and here, this should be a pretty simple equation now, solving for x. Really, x here is saying what power of 3, right, will give you 27. And that's 3 cubed will give you 27. And you can just go up through and go like, okay, well 3 squared gives me 9, 3 cubed gives me 27. And then you have your answer. Okay? So you get x equals 3 as your answer. Okay. For problem 47, we want to write log of a equals b in exponential form. Okay? So again, we want to undo this log expression, okay? Or this log equation. And this is this is simple, right? We don't have a million logs attached to this thing. So we can just use circle trick. We have log, and remember when the log doesn't have a base, it's base 10 by default. And so we can make this 10 bigger, put the a over to that side. The b goes in the exponent on this side. And so this becomes 10 to the b equals a. Okay? So again, it's that idea of circle trick. Moving on to problem 48, we want to simplify the natural log of 1 over e squared. It's actually kind of funny because I had I believe like this exact same natural log that I had to find what the value was, and that was just a little part of one of my physics final problems. So it was kind of interesting to see something like that. And I was like, wait, I just scripted that for this video. So anyways, how do you solve something like this? Well, you need to understand a couple things about natural logs. If you have something being divided in the natural log, you can rewrite it as the natural log of 1, or in this case, the natural log of 1 minus the natural log of e squared. So you can separate it and make them in different natural logs. If it's division, you subtract. If it's multiplication, then you add. And that's something really important to note. Okay, and we'll actually have some more practice with that, I believe, in the next problem, but we'll see. The natural log of 1 is 0. Here's why. Because natural log has a base of e, right? So natural log of 1 equals x. Well, natural log is a base of e. You do circle trick, make the e bigger. You have e to the x equals 1. Well, what value of x will give you 1 here? Well, it'd be 0, right? Because anything to the 0 power is 1. Okay, that's just a little quick way of showing that. I'm sorry if I went too fast. But anyways, you can rewrite this here as you can bring the 2 out, and this is 2 natural log of e. Okay, well the natural log of e is 1, and here I'll show you that with just a little bit slower. We have natural log, and that's basically the same thing as base e, right? It's the idea, and we have that equal to x. We make this e bigger, we drag this over to the other side, this becomes the exponent, and now we have e to the x equals e. So what value of x is going to make e? Well, that'll just be 1, right? So this ends up just being 1, so we have 0 minus 2 times 1, and we know that's negative 2. Okay? Here's that other practice I was talking about. This is for problem 49. we want to calculate log of 5 plus log of 4 minus log of 2. Okay? Well, first off, let's just combine these two logs. It doesn't matter where we start, but we'll start with log of 5 and log of 4. If we combine these two things into a single log, it's log of 5 times 4. Okay? We subtract log of 2. Well, we can, again, combine these two things again, because this is being subtracted, so we can just divide. So we have log of 5 times 4 over 2. Okay? Well, we know that log of 5 times, well, we know 5 times 4 is 20, and we know 20 divided by 2 is 10. So this is the same thing as log of 10. And what is log of 10? Well, it's actually kind of the same thing that we just dealt with natural log of e in the past one. We know that the base of a log is 10 if there is no base that written there. And so we have log base 10 of 10 equals x. We do circle trick. Make this 10 bigger, put the 10 over to the other side, the x goes to an exponent, and we just get 10 to the x equals 10. What do you think that value of x is? Well, it'd just be 1. Okay, so you can actually, as your final answer, write that log of 5 plus log of 4 minus log of 2 equals 1. Okay, that's it. Just combine them with that multiplication division rule. Okay? And the last problem that we're going to do is problem 50. This is a problem where you can't do circle trick. This is why I said simple logarithmic functions. Okay? This is not that. It has multiple logs on each side. Okay? So this problem says we want to solve for x where we have 1/2 log base 3 of x equals 2 log base 3 of 2. Now, the thing is here, we have the same base on both sides of the log. Okay? And this is actually basically the same thing as common bases. Okay? And the idea here is that, well, let's just simplify these log expressions a little bit. Let's actually make them a little more compact. We'll put the 1/2 here back in the exponent on the x because it's being multiplied by that log, so that's something we can do. And we'll do the same exact thing with this too. We'll put it in the exponent over here. So we can rewrite this as log base 3 of x to the 1/2 equals log base 3 of 2 squared. Okay? We know that, you know, if you have log base 3 of, let's say, 4, it needs to be equal to the log base 3 of 4, right? It's not going to be equal to log base 3 of 5 or log base 3 of 6. What it's saying is that what this is saying is that the arguments of this log, since it has the same base, the arguments which I've highlighted here, okay, that's what that's called in the parentheses. It's called arguments, right? They need to be the same in order for this equation to make sense. So, and this is the same exact thing as common bases with exponents. We know that x to the 1/2 needs to equal 4. Okay? And so, all we have to do to solve this, okay, all we have to do to solve this is just square both sides. Okay? If we square both sides, we get that x equals 16. Okay? And that was our final problem. Okay? So I really hope that this video helped you guys out. You know, if it did, make sure to subscribe. I have a bunch of other content on here that I really think could help you out, and I also make videos about my own college journey, just going through my different classes and different college life things. So I really appreciate it if you did subscribe. Leave a comment if you are having any trouble on the video, or if there's anything that I can help you with, because I may have explained certain things too fast, and I apologize for that. So yeah, leave those questions in the comments below. And yeah, I hope this video helped, and I'll see you soon.